Hi everyone. So we just finished nucleophilic addition, where you take a nucleophile, add it to the carbonyl, and then that carbonyl turns into an OH group. All right, so after a second protonation step anyway. Okay, so usually you'll see H2O or H3O plus dilute as a workup step. Now we're going to try something that's a little bit different, and this is if you happen to have a carbonyl group with a leaving group on it, such as this chlorine could be a good leaving group as chloride. So in this kind of mechanism, we follow the same steps as before. Nucleophile comes in and attacks and then releases electrons up to the O. And then you make what's called a tetrahedral intermediate. Okay, so we did this as well up here. Here's our tetrahedral intermediate. But instead of neutralizing this oxygen in the next step, we end up with some kind of an elimination that kicks out the chloride. So can you picture the arrows that we would need in this step to make these two things? Well, we start with the lone pair on the O, and one of those lone pairs can come in, regenerating this carbonyl pi bond, and then the chloride can leave as a result. Okay, so that's the collapsing of the tetrahedral intermediate to make something more stable. And then we have this Cl, which is a leaving group. All right, so we added the curved arrows. This is called an addition-elimination rather than just the addition we saw. This is an addition. This is addition-elimination because of the second step of having a leaving group. You remember E1 and E2 maybe from first quarter where we had a formation of an alkene. So same thing here, formation of a pi bond and a leaving group. Okay, so let's say that if we have a nucleophile that's strong enough, it will drive the reaction forward, and also we'd want a good leaving group as well. Now in this last question it says, which of these reagents as the nucleophile would make this reaction reactant favored, meaning no reaction? Okay, so it's good to think about what your nucleophiles generally are. They're generally strong nucleophiles. So basically this question is asking you which of these is not strong. So let me give you a minute to think about it. And just to give you something to work on, this first one would be hydroxide. Remember, sodium is the spectator ion, so we don't really care about that part. So the OH minus, I know, is a strong nucleophile. We've learned that before. So it's a strong base, it's a strong nucleophile. So go through these and maybe consider base strength as one possibility. Steric hindrance is another one. We want less steric hindrance to be a good nucleophile. Let me know what you think. All right, guys, so we're back, and I already said hydroxide is something that I know is a good nucleophile because it's a strong base. So I want to use that to also say this amide, sodium amide ion is very, very strong base. It's even stronger than hydroxide. So its conjugate acid is weaker. So therefore, this is going to be a strong base, so this is going to drive the reaction forward. This is a Grignard reagent, and this is going to attack as a nucleophile. It's a pretty strong base as well. Bromide comes from hydrogen bromide, for example, is its conjugate acid. We know HBr is a strong acid, so we know Br minus is a weak base. All right, so here this is actually not such a great base. We do know it's a good nucleophile because of its size, but in terms of base strength, it's the weakest base here. And then over here, and it's also fairly large nucleophile as well. So NaBH4, we know that the BH4 is a hydride ion. So you could think of this as H minus. And that's, it's on your list as not such a good nucleophile because it's small. But so it's not very polarizable. But for these reactions where it's attacking a carbonyl, it's actually more important for it to be a strong base than it is a good nucleophile like for SN2. So, and later we'll learn that this is what we consider, there's something called a hard-soft theory. And a hard electrophile is this carbon right here. It's sort of considered a hard electrophile. These smaller nucleophiles react better with this carbonyl group than a larger, softer nucleophilic bromide. So actually, if I have to choose for a carbonyl, it's better to go with a smaller, stronger base. So that's something you didn't know before, probably. And then finally here, organolithium is just like Greenyard, so it's going to be a strong base. The methyl group is going to be the one that is the nucleophile. So I'm going to highlight my nucleophile. And so for all of these, just based on base strength alone, it would be bromide. And also because it's polarizable, it's not as compatible with carbonyl groups as electrophiles. So reactant favored or worst nucleophile would be the NABR. All right, let's practice our addition-elimination mechanism. And there's actually a couple of ones that I want you to know. Starting with one that we skipped, which is actually this one here. We talked about adding water to an aldehyde, and actually we didn't talk about it. I told you to skip it for now. Let's do this now. This concept of having a weak nucleophile, just like sodium bromide, was a weak nucleophile in our last example here. There are ways to react this with weak nucleophiles, but we have to do something special first. So either if this is weak here, and they're telling us that, but we know water's a weak base, a weak nucleophile. In that case, then we need to make this more enticing for the nucleophile to react with it. Otherwise, nothing will happen. So we usually add a little bit of catalytic H3O+. Catalytic means you're just adding a little amount, a few drops, just to get it started. And so you would take like a bottle of concentrated H2SO4, sulfuric acid, and you would add some of that to your reaction. Doesn't have to be stoichiometric. So what we usually do is show that in brackets, just to say there's a catalytic amount. So that's what we'll use to make this more enticing for reaction. So how we do that is we're going to use the lone pair to attack an H plus or H3O+. That will make us an activated carbonyl group that looks like this. Okay, that activated carbonyl group now has a very positive carbonyl carbon because of that positive charge on the oxygen. By induction, it pulls even more that charge. So what I'm going to do now is have the water attack this carbonyl, because now that carbonyl seems a little more positive than before if there was no acid activation. So here's my water that is going to be my nucleophile. Now it's much more attracted to this carbonyl group. So it comes in, and then we show that addition. So here's I'll follow my color scheme. So I have the carbonyl turn into an OH group, and it's already protonated, see? So that's different from before. It's already protonated because of this acid catalyst step. Okay, so all right. Here's my water, and that makes this positive. Now you think this looks like a good leaving group. It leaves, but that means we're just going backwards. So to go forwards, then we just need to neutralize this, and then we will end up here to something we call a hydrate. And notice it's two hydroxyl groups on the same carbon. All right, so to do that, I will grab another water and do a proton transfer. As usual, anytime you want to neutralize, look at what solvent is in solution and use that. Okay, that gives us what we call a hydrate. You probably have heard of hydrates before, at least in Gen Chem, like, Epsom salts, magnesium sulfate, heptahydrate. These are, or sodium sulfate is a hydrate. You guys use that in lab as a drying agent, and it grabs water and then it puffs up. With a lot of water around, this functional group, the carbonyl group, turns into this. All right, so I would say maybe just highlight that part. Yeah, so I would think of it like this. This carbonyl right here, as a hydrate, turns into something that looks like this. Okay. And there's this equilibrium where usually the carbonyl group is more stable. It just depends, though. If there's more water around, then it pushes the reaction to the right via Le Chatelier. If you dry it, put in a drying agent or boil off the water, it will drive the reaction back the other way. And you can see that their potential energy is similar. But to get over these steps, small delta G's, so that's how we do it. but it's reversible. So it really just depends on using Le Chatelier to manage which side of the equilibrium to favor. Will adding water, removing water, push the reaction forward? Well, to push the reaction forward, we want more water. So we want to add water to push it forward. And then if you try to isolate this by distillation, usually we purify things by distillation. It doesn't work in this case because water is being boiled off, and that means you're removing a reactant that pushes the reaction back this way. So it doesn't work because of Le Chatelier. Chatelier. I need to review my French. Le Chatelier distillation will removing reactant, which is water in this case, will push the reaction to the left. And so that's why we can't isolate a hydrate then. If we need to push the reaction that way, it's not going to work. So now I'd like you to see how that plays out here, where we replace water with an alcohol, simply an R group, right? Water is HOH, alcohol is ROH. So by doing that, we have the same exact mechanism. We just have to carry this R group with us. So So what I'd like you to do is try to think of the mechanism for halfway through, which is exactly the same as for the hydrate, except we have an R group to deal with. And what we're going to do is make something called a hemiacetal, which is like a hydrate, except instead of two OH groups, I have an OR group, which comes from this alcohol. Okay? And then after we make the hemiacetal, then I'd like us to go from the hemiacetal all the way to the acetal. And the acetal is where we have two OR groups. So these both come from the first alcohol and then the second alcohol make these two ether groups on there. Okay, so why don't we do this? I'll give you a chance to do this first one, where you follow the exact same thing we did as with the hydrate just now. Do the activation step with the acid, nucleophilic attack, followed by proton transfer. And you should be able to do that. Yeah, let's give that a try, and then we'll go over that together. Okay guys, so the first step is we need to activate our carbonyl group to make it more enticing for the alcohol to attack. And then my alcohol is going to see that and say, okay, I really want to go right there. And once you do that, then you've got your OH group already, but then you've got your alcohol group that needs to be deprotonated. And after you deprotonate it, and with what? You have to look at the reaction and ask yourself, what is in here? And it doesn't show waters in here, it shows alcohols in here. So you got to just use whatever is in the solution, okay, to do your dirty work. Okay, all right. So we got this guy, and now we've got our hemiacetal. See that? An OR group and an OH group. That's what makes this a hemi. Hemi means half. Acetal. Okay. All right, after that, let's take our hemiacetal, and we want to go to the full acetal, which means I need to have another alcohol equivalent. So I need 2 moles of alcohol for every mole of carbonyl, and I still need acid catalyst. And my product, so here, acid catalyst, and then a second alcohol group. And I probably should have used a different color for an alcohol group so you could see. Let me try that now. Here's my alcohol, here's my alcohol, here's my alcohol. So I have one of them, and now I'm going to make a molecule with 2 of them, meaning it's going to be R, R, O, R, and OR. This is my acetal. So that's my goal in the second step. Now I'd like you guys to pause it and see if you can follow the same steps we did here to get the acetal, but it's going to be a little bit different. So see if you can at least try it first. Notice that our goal is to get rid of an OH group and replace it with an OR group. We already have one ether group. We need another one. So I want to try to lose this guy. Okay, keep this one, and then have this one come in as my second OR group. That's the main strategy. Okay, go ahead and give this a try. All right, guys, so our strategy is to get rid of this OH group, and we want to add this OR group. Okay, so what I want to do is turn this OH group into a good leaving group. So that's what the acid is going to be for. So my first step is similar to how we activated the carbonyl with acid. We're going to turn this into a good leaving group. So that will get protonated here, and then I'll have my OR group hang around. Okay, at this stage then, I want to have this leave, and you would imagine making a carbocation here. Now I could do that, but oftentimes we want to show the more stable resonance structure, which does not disobey the octet rule. So in this step, I'm actually going to bring these down and then kick this out. Sort of similar to our addition-elimination step that we learned earlier right here. It's very similar to that kind of idea, okay? So again, I could show the carbocation, but this is the more stable resonance form. It's going to be this guy right here. All right, so here's the addition-elimination, okay? So I added the OR group, and now this is a tetrahedral intermediate, and then I'm going to lose the leaving group. All right, at this stage then, you can imagine that this carbonyl carbon is my electrophile. And now I'm going to be able to do a nucleophilic attack in the next step. So let's do that. The next step, I'm going to bring in ROH, and I'm going to attack it here. All right, and now we have just a regular nucleophilic addition on this carbonyl. So the next step is going to be to have an OR from before and the new alcohol, the second equivalent of this alcohol that attacked. Okay, so right here. All right, now again, this could leave because that's a good leaving group. So all of these steps are actually reversible, by the way. And so we drive it forward by Le Chatelier's principle. We make sure there's a high concentration of alcohol to go forward. Okay, after that, I need to not make this leave, right? I want to keep both OR groups on here. So my goal would be just to get rid of this H. So I just need a deprotonation step at the end. So what do I have in solution to deprotonate this? If you look, I just have these two things. So I'm going to bring in another alcohol group, and then I'll deprotonate there. So that's how I end up with two OR groups. All right, I hope that makes sense to you. So pretty much you're looking at what you have, you're looking at what you need to get to, and you're following a mechanistic route that gets you there. And we need the acid catalyst in order to make these groups leave.